I'm Evan Sherwin, postdoctoral researcher at Stanford University, working with Adam Brandt and many others. And Jeff Rutherford just gave a fantastic presentation on our work on aircraft. So following up on Jeff's work, the big question here that I'm really interested in is well, what can satellites tell us, and what, at least at present, can't they tell us? And then I'll touch at the end on this question of what fraction of total emissions can satellites see. So basically everything I'll be presenting here is in our preprint, which was posted a couple weeks ago on Earth Archive. And yeah, you can see a number of wonderful co-authors here. So yeah, we decided to go out and test, as Jeff illustrated. This is my sort of cartoon of us turning the methane level up to 11 to test out satellites. And we tested out every single satellite that we were able to. So GHGSat, I'm glad to see a couple folks from GHGSat on the call, as well as Landsat 8 and Sentinel-2. Those are satellites that are government satellites for the most part, and basically up and orbiting all the time, covering the whole Earth's area every couple of weeks. WorldView 3, another private satellite, as well as PRISMA, which is a European Italian Space Agency satellite. And I've got to give a shout out here to Luis Guanter and his team at University of Valencia. We wouldn't have been able to test out PRISMA and WorldView 3 if it hadn't been for their very significant efforts. I should note, because there's a lot of discussion about the TROPOME satellite or instrument on Sentinel-5P, that we did not test that because we just didn't feel that we could get up to 10 tons or higher per hour of methane, which we thought would be necessary to test that out. So a bit of background for those, yeah, just on these satellites themselves. So there are two main types that we tested. I'll call them targeted and global, and one can talk about the different terms for these, but essentially with GHGSat, WorldView 3 and PRISMA, and the C2 is here just because that's the particular instrument we tested, but there are now 5, as Jeff mentioned, in the C constellation and 1 in the earlier D constellation. And these are just satellites you have to point somewhere in order to see. Whereas with Landsat 8 and Sentinel-2, they'll cover pretty much any area on Earth, just sort of passively, like just a constant stream pointed in the same angle. And then there's Sentinel-5P, which again we didn't test, but that covers the whole world every day. So that's pretty remarkable. And you can see the trade-offs in terms of swath and revisit time. And then I didn't include this, but resolution, of course, with a smaller swath, you get much higher resolution. So we really, yeah, tried to have as many teams on board as possible analyzing the data from these satellites, because in many cases the data were available to multiple teams. So why not have multiple teams try to estimate methane emissions from that we were releasing. So Kairos, I'm happy to see we've got a representative on the call, Daniel Jacob from Harvard University, GHGSat, SRAN, the Dutch Space Agency, Sudhanshu Pandey in particular, who's now at JPL, NASA Jet Propulsion Lab, as well as University of Valencia, Luis Guanter, Itziar Aracolis Lachate, Javier Corano, Elena Sanchez Garcia. Yeah, so glad that we could have so many wonderful participants on this in this really unique study. So, as Jeff mentioned, we used a staged unblinding process here, but in this case we couldn't collect enough data points to do the third stage where we unblinded half. In some cases, we only got 1 data point per satellite. So we just had the first stage, which was completely blind. The only thing that the operators knew was roughly where to point the satellite. And then the second stage we gave in situ the wind measurement from the 10-meter anemometer, speed and direction, and the exact coordinates of the release point. So yeah, as Jeff highlighted, we used the Ehrenberg setup, liquefied natural gas trailer. We had to heat this gas up because it was really cold, and put it through a big shipping hose into this metering trailer, where it was released out of a high stack. We were hanging out over here by the wind meter. Yeah, so this was minus 160 degrees Celsius, and this is a picture of the team. This is Tyler Farmer Mullen, who Jeff mentioned, the technician who's really been with us through thick and thin through this entire past year. Who's single-handedly, well, he's made so many things work, as have the other technicians at RIDE. I really appreciate their work. This is a close-up of the release trailer, which, as Jeff mentioned, we've got a couple different sizes of pipes. So we got this big 8-inch for the really big ones, going down to 2 inches. 2 inches is the smallest we can do for the quadratherm meters we used. Then we had a 1/2-inch pipe as well for the smallest releases we did using a Coriolis meter. Although for the satellites we didn't use that one. And yeah, so all the satellites we gave all the satellites about 4 tons per hour of methane for at least one of the releases. In some cases, we got substantially more than one. And these are the methane retrievals from each team analyzing a given satellite. So for Sentinel-2, 4 teams analyzed all the results, all the data. So Kairos, University of Valencia, SRAN, Harvard. And you can see that the shape looks kind of similar in all cases, but there are some differences too. So they're clearly looking at the same thing, but they are also looking in different ways. And you can see some substantial variation in the volume estimates too. So the actual volume that we were releasing was 3.5 tons, and there's some uncertainty around that due to metering and flow variability, which I'll display in more detail in the next slide. And yeah, so these are the estimated mean values. I include the uncertainties again on the or 2 slides down. And we also have this is the wind vector, which you can see, like, so this is the average wind a minute before the overpass. And you can see, well, that lines up there, but actually the winds have probably been changing in terms of direction. So there's a lot of complexities here. And another thing that really jumps out, and there's like, we could spend a lot of time talking about this particular figure. And I should say that the color scale is methane enhancements in identified areas of a methane plume. So there's a couple. The question of sort of identifying a methane plume is an important part of this as well. And Jan Zhang, who I'm not sure is on the call, but she's doing some work that hopefully we'll be able to talk about soon, really digging into this question of, well, what can and can't we see? So, and the other thing that we see here is that these releases are all about the same size, but the shapes here, the plumes identified, are in some cases quite different in size. So PRISMA, GHGSat, they see a much bigger methane enhancement area than, say, Sentinel-2 and Landsat 8. And one of the main reasons for that is that these are just much more sensitive instruments. The true extent of the plume is much longer in terms of, well, how does one define a plume? There's some methane enhancement going out much further than really all these instruments can see. So here's the results in terms of detection. So we've got all the different satellites on the top and the different teams analyzing the satellite data on the bottom. And we see here the true positives, true detections, as well as the any false negatives, something that we were emitting, but it wasn't detected, true negatives, correctly identifying when we weren't emitting, which we did in one case for Sentinel-2 out of 7 total overpasses. Then false positives, which there were none in this test, and then what we're calling filtered retrievals, where there were either clouds or something, the image was clipped, so the retrieval wasn't attempted. So this is a case where there just wasn't an attempt to take a measurement due to some factor related to the environment or the raw collection of the data. And then there were a few instances where a satellite passed over, but it wasn't tasked for some or another technical reason. And what we see here is that in total, 71% of overpasses were correctly identified, and there are some false negatives. Since we had so many measurements of Sentinel-2, we wanted to characterize the minimum detection limit. We actually went below what some thought was the minimum detection level, and to me this looks really good. So here we have a parity chart, and I realize this meta talks. Yeah, this is going to be an extended session. I expect the Q&A is going to go for a while too, so thank you for bearing with us. So here we have the true metered value here on the x-axis, and this again is accounting for uncertainty, which is considerable. It's not negligible, but it's also a lot smaller than the uncertainty in the y-axis. This is 1 sigma confidence interval. So if you want a 95% confidence interval, basically multiply all these uncertainties by 2. And here we have the estimated emissions from each of the teams. So what we see here is there's of course a lot going on here, but really one of my main takeaways is that the scatter that we see here is very similar to what we see in percentage terms to aircraft. So aggregating across all the satellites, which of course has some statistical limitations, but just to give a general picture, 78% of all the measurements here are within 50% of the metered value, plus or minus 50%. For the Kairos Aerospace Controlled release we did back in 2019, released in 2021, it was 79% of releases that were quantified, so not including the non-detections or the negatives, are within plus or minus 50%. So this, I think, is a really promising sign. And we also see fitting a line to these results, again, fitting it to everything. So it's just giving a general sense of the quantification. This is a slope of 0.85, where the ideal slope is this black dashed line of 1. This is looking pretty close to unbiased, and the R-squared, this is an R-squared for a fit with a fixed intercept, just because without that it would just try to fit pretty much a straight line. But and so the R-squared has a different interpretation in this context than one with a floating intercept, but still this is a pretty high R-squared value. We see Sentinel-2 goes all the way down to 1.4 tons per hour. 3 out of 4 teams that analyzed Sentinel-2 data detected that, and GHGSat detected the smallest thing that we gave them, of 100 or 200 kilograms per hour, and we can't even see the error bars here. Adam likes to joke that they somehow hacked into one of our computers, but no, this was a single blind test, and GHGSat in all 3 points that we were able to collect got very close to the actual value. And really, but again, really all these teams are demonstrating what I think is very impressive performance. So here we then we released the second stage of data. So gave the 10-meter anemometer wind data, wind speed and direction, as well as the pin drop coordinates of exactly where this release stack was. And the teams all sent in another set of estimates, and the parity line, the fit line, is literally on the 1-to-1. So, and the R-squared improves. So this is an indication that with improved wind speed data, this further increases the capabilities of satellite-based remote sensing. I should note that all the teams in the first stage did the same thing they do in the field, which is use wind reanalysis data, which are not based on measurements. They're very useful for many purposes, but they're pretty noisy. So if we can, and methane concentrations in the atmosphere are just about directly proportional to wind speed. So if wind speed's off by a factor of 2, then that means quantification estimates are likely to be off by something like a factor of 2. So this is a real indication that if we can somehow improve either improve wind reanalysis data or develop methods of quantification that don't require wind speed as an input, such as computer vision-based methods. There's really cool work coming out of NASA Jet Propulsion Laboratory on this front. That I think would be really impactful. So what fraction of total emissions could these satellites see? That's a big question that so many of us are asking ourselves. And I can't answer that question fully today, but I can hint at least in an extreme case, what we could see with these types of satellites. So this is taking data from Chen, Sherwin, et al. Yulia's paper. Yulia's on the call and gave a fantastic meta talk not long ago, presenting our results from the New Mexico Permian Basin. And so this is a cumulative distribution function. If we look at the plumes, the individual plumes, not averaged over individual emission sources, because at a given set of overpasses, the satellite would be seeing the plumes, not the averages. If we were, and I should say that this paper estimated that the fractional methane loss rate of the New Mexico Permian Basin during the study period was about 9%. So that's quite high. This is only for the emissions that were, if we only include the emissions that were directly measured, it's about 7.4%. So that's what I'm showing right now. The breakdown. So above 100 kilograms per hour, if we had an instrument or a set of instruments, realistically, we need a constellation that could survey the whole area that we surveyed, or that Kairos Aerospace surveyed, and then graciously collaborated with us. If we were to survey if there were to be a survey of the entire New Mexico Permian Basin during the same time period with an instrument of 100 kilograms per hour minimum detection limit, we'd expect that to see upwards of 90% possibly of total emissions, or ballpark 90%. And in my preprint, I've got the more exact numbers. I should have put those in here. But if we were to go up to 1,000 kilograms per hour, even then, that would be able to see more than a quarter of the detected emissions from this campaign. And even 5,000 kilograms per hour would be a not inconsiderable fraction of the total. So some takeaways here. To me, the main takeaway here is that these methane sensing satellites work, in my view, quite well. All the satellites saw most of the emissions. Most of the emissions that they were given. There were no false positives, and the quantification performance in percentage terms was comparable to what we see with aircraft. So, as far as next steps go, I view this work as an important milestone in our assessment of the capabilities of satellites, but by no means the conclusion of it doesn't tell us everything we need to know. We really, ultimately, if we're going to rely on these satellites for global methane mitigation, monitoring, we really need to get the types of graphs that Jeff was showing, get enough data points to characterize the quantification error for individual satellites and the minimum detection capabilities, ideally under field realistic conditions. So multiple types of terrain, places with less ideal weather. And a real kicker here is if we could test in unknown locations, then that could really give us a better sense of how that's sort of a true field test, because right now the teams all know where to look and might be able to see something with a little more sensitivity than if it's just a blip in a giant area where there may or may not be methane emissions. That logistically would be a lot more difficult, but I think it would be very valuable. And yeah, next steps. Finally, we should be using these satellites and the ones that are coming to reduce methane emissions. So with that, I'd like to once again acknowledge our funders and collaborators. So ExxonMobil, the Stanford Strategic Energy Alliance, and the Stanford Natural Gas Initiative. This just wouldn't have been possible without funding from all three of those sources. as well as I've got to add the just fantastic technical support and scientific support from the team at ExxonMobil. And we, yeah, then some, that's from an old one. Rawhide Leasing. I didn't talk about Kairos Aerospace today, but I'm very grateful to Kairos Aerospace, and glad to see some Kairos folks on the call. And I did talk about the New Mexico Fermion papers, so we're okay. And then the fantastic team that worked on this project. With that, I will conclude, and let's have a Q&A.